Hello again, my name is tbaldridge. I'm a developer for Cognitect, and we're going to talk a little bit more today about the macros of Core.Async, how they work, and some of the ideas behind them. There's a previous video, if you want to take a look, called Deep Walking Macros, that kind of discusses how we build macros that do more advanced work than just simply doing some operations on the expression, on the top level expression that we hand them. So with that, let's dive back in today. So to start with, when we ended last time, we had a set of multi-methods that looked like this. We have parse sexpr with we take some arguments, the form and the body, and then we have this context we pass around. Now this is the problem, and we see it expressed right here in the if, and that is somehow we expect parse item to add things to this context as we go along. And that could be, for instance, doing some analysis on the data, or it could be building up a some sort of data structure that we want to analyze later on. But the problem is if you see here, we're not taking the output of parse item and doing anything with it except giving it to a hash map. That is, the context that is modified in this first parse item is not handed in as the context for the second. This is a problem. This basically assumes that we either are going to only read from context, or that the context is going to be mutable in some way. And that's what we did later on. We ended up having to an atom to the parse item as a context. And that works, but now we get into a whole other set of problems with the fact that our analyzer is inherently mutable. And that gets to be a little bit ugly. So is there another way to look at this sort of thing? For me, what started making sense was when I began thinking about currying and partial application. These are two separate things, but let's look at currying first. So currying is a way of looking at functions in which every function in your system, or the curried functions specifically, take only a single argument. So we could have a we'll do a function called add today, and we can hand it a single item, and then we could add one to that. Now this is pretty useless, right? I mean, what good is a function if we can only hand one argument? What are we going to do? Pack things up as a data structure and hand it in as a single argument? That seems a little bit weird. But what currying does is says, no, there's another way we can deal with multiple arguments to a function, and that is by having the first function return another function. So to make this a little bit cleaner, we're going to turn this into a def and have fn of x, and then we're going to nest yet another function in here called with another fn of y, and now we have our normal function that we would expect. So if we evaluate that on the right side, we can see that if we add if we have add of 42, we get back a function. And if we try to add 1 to that, like this, like we would normally call a function, we get wrong number of arguments. So what we can do is call the next function with 1 as the argument instead. And we evaluate that, and we get 43. And we could do this in infinite length. We could just continue to have more and more functions. So what's the takeaway from this? It's basically the idea that we don't necessarily have to know all the arguments when we call a function. We could leave some arguments up to someone to say, later on, if you want to give me this argument, you're free to do so. There's a function in Clojure called partial that does the same sort of thing. So we can say this will be an incrementer. Yeah, we'll just call it incr. And we'll do partial plus 1. And what we get is let's call it, and it increments like this. So what partial does, this is called partial application, and that it converts a function of a certain number of arguments to a function that requires less arguments because you're providing some constants or half the arguments now. It's partial application. Now all this really does in Clojure is wrap up the function within another function that has these values as closures. But in some other languages, we can get a little more fancy with that. And if you want to read up more on this, look up perhaps ML or Camel or F Sharp. They all use curried functions, I believe. And if I remember correctly, Haskell uses something along the same lines to do lazy evaluations and perhaps reorder the execution of a function based upon what arguments you give it. I don't know that for sure about Haskell, but I believe it works something like that. So anyway, back to the subject at hand. If we were to work with hash maps a little bit differently, we could get them working in this sort of world where we would provide the operation that we want to do to a hash map, but not actually execute the operation on the hash map yet. So let's call this R-assoc for reverse assoc. And the reason we're going to do that is we're going to give the key and the value first, and then the map later on. And what we're going to return is a let's see here. How do we want to go about doing this? Yeah, that'll work. So we'll do assoc map k and v. And that'll work fine just like that. So what we can do now is we can have a add name or add me. We'll do this, and we're going to have that called partial R-assoc, and the first argument is going to be name, and Timothy is the name. So if we evaluate both of these, we have now had this function called add me. And if we call add me with any hash map, it adds the name. But this add me is now something we can kind of just move around and treat it as if it were a value. We could pass it to something else, for instance, and do all sorts of weird things with it, right? So what does this give us? Well, what this gives us is the ability to thread the result of one of these R-assocs into another. Because what we've done is we've genericized the operation to just being a function that takes a hash map and returns a new hash map. So let's look at that. Let's say we'll look at how we will execute this function first, and then we'll actually build the function. So we're going to call it thread it. This is going to be like a function version of the threading macro in Clojure. So we're with a little bit of extra ceremony, we can accomplish with functions what Clojure does with a macro. So partial R-assoc name Timothy. We're going to do it again. Last name Baldridge, and then partial R-assoc, and we'll do state Colorado. All right, so now of course if we execute this, we don't have thread it. But it should be pretty easy what we need for thread it, and that is we're going to take any number of arguments, or functions in this case, right? Functions. And we're going to reduce over them. And we are going to have some sort of function here that takes an accumulator and a value to do something with. We're going to start off with a hash map, and we are going to go over all of our functions in this reduce. So for each call here, we're going to change v to the name of f so we know exactly what it is. We are going to pass in f and give it the accumulator, and then that will become the new accumulator. So we're just using reduce here. For every one of these functions, we're going to call it and transform the accumulator over and over again. All right, now if we do thread it, boom. State Colorado, last name Baldridge, first name Timothy. All right. Now, what if we went yet another step farther with this, right? What if we said, now all of these operations want some sort of function that takes a hash map and does something to it, right? Well, that means that thread could also take a function, right? We've hard-coded this hash map here. Well, that's not composable. So let's define this as returning a function that has an argument called initial, like that. So now if we call thread it returns a function, which we can then parse an initial. We can hand that function an initial value, which in this case will be a hash map, and we get exactly the same thing. Great. So now what? Now we can compose this, right? Because we could go like this here, and we could say defn add personal info, and then we can have defn add job info and do the same thing. Job and so I'm a developer. All right, great. Now we have these two ones here, right? Personal info and job info. And these two can also compose. So we can thread it with add personal info and add job info. And then if we call this, well, hey, we didn't name this right. There we go. Hey, it's another function. So if we call this, and now we're just, it's turtles all the way down, right? All right, there we go. So job as a developer in the state of Colorado. My last name is Baldridge, first name, same thing. All right. Now, those of us who are perhaps ex-Haskell developers or something along that lines are probably screaming right now at the top of their lungs, this is a monad. Yes, it is a monad. This is called the state monad. To be honest, I don't really care what it is. The fact is that it allows me to write analyzers and compilers in a functionally pure way without having to worry about perhaps mutability or that sort of thing. There's a whole lot of things that could be done with this, but in the case of these deep walking macros, we have something. We take this a little bit farther, and that is if we look up here in our parsing of the if, we have context, right? And what we end up doing is creating a macro that kind of does the threading for us, that takes the output, that takes the functions up and wires them all together. So in these deep walking macros, the parse item that we're about to look at doesn't return a function that returns a hash map. It returns a function that returns a vector of an item and a hash map. And what that allows us to do is to assign IDs to expressions. So what I want is something like this, and this is what we use in Core.Async. I want something called, I have this thing I call GenPlan. You can call it whatever you want, right? But what it allows us to do is have test ID is parse item of test, and then is parse item. Let's see, then ID, and then else ID is parse item of else. And then this is this binding form, and we can use these IDs as arguments to the other expressions that come after them, or down here at the end we can construct something like this. Type is if test ID, or test is test ID, then is then ID, and else is else ID. So we're gonna look at the source code for this stuff in just a little bit. But what this GenPlan allows you to do is that you do not see context here anywhere. There is no context. So behind all of this is a hash map that we can associate data into, we can remove data, we can build up contexts, we can set IDs for things, and each item can still, even with that context being managed in the background, can still return an item, some return value, be it a hash map, or in the case of Core.Async, it's often a symbol that represents an instruction, and we can use those to construct something. So the output of this GenPlan here, this hash map, would end up being somebody else's value that they would use in another GenPlan. All right, so that's pretty abstract. So let's get into this a little bit more. So let's go into Core.Async. So we're going to be working in impl IOC macros today. All right, and we need to restart our REPL. So this will take just a second. So we'll play around with this a little bit, and then we'll see how we use it. And here. Sorry for the setup time here. Oh. Yeah, I am not getting my key bindings right today. All right, there we go. Okay. So if we compile this, excellent. And we can drop into this namespace there. All right, we're good to go. Okay, so as I mentioned, we have this thing called GenPlan. And what GenPlan allows us to do is to bind up these monad things for us. So let's actually go back to a our workspace that we were at a little bit ago and play around with this. So we have this thing called a SSA Plan that says go into the context that's hidden behind the scenes and associate something into it. And this follows the normal SSA pattern. So test, and we're going to associate into that hello. Now that returns a function, right? And just like I mentioned before, if we hand this a hash map, we get two things back, right? So a SSA plan returns as the value hello, the value that we were handed here, and it returns a new context that has associated hello in as the test. And we see that over here on the right here, right? Okay, so now we can start using GenPlan for this. So the associated value is the return value of this here. And let's see here. Yeah, we got an extra parenthesis. There we go. That was the problem. All right. So it says wrong number of args passed to GenPlan. We have to say what we want to return from this. So let's do something else. Let's say let's create a new string. Value is, and so if we execute this, we get back a function. Now this function, like everything else, right, takes a hash map as the starting point. So if we handed the hash map, we get back value is hello, and our context is hello. Because up in here, we associated into that context, into the state, this test and hello, and the value returned by a SSA plan is hello, and then we create a new value, which is the new value is the concatenation of these two strings, right? Okay, so there's a couple other primitives that we have. So let's say we have a collection of things that we want to do. Let's say we want to have test, and then we want a number. So we want to have a nested tree, and we want a different node of 1, 2, 3, 4, and 5 for each one of these. Now, our first plan would be to do this, right? So we're going to do for x in range to 5, association plan, right. If we execute this, we get an error. Lazy sequence cannot be cast to an IFN. Why is that? Well, what does GenPlan expect as the second argument? It expects a function that is looking for a hash map, right? That's all of these functions. If I remember my monad tutorials right, it's looking for a monadic value, but that doesn't really help us. So it's looking for a function. It's looking for a function that it can hand a single hash map to. So we need something that converts this. And the Core.Async IOC stuff also supports this thing called all, which will say you are going to give me a seek of functions, and I am going to return you a single function that threads the context through all of those functions, right? So if we execute this, we get another function back. Interesting. And what happens if we then execute that function as the way we execute all these monad functions by passing in a hash map? And what we get is hello, 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 test, hello. And that happened because I didn't put a little x here. And let's pretty this up a little bit more by concatenating the string that gives the value. So now if we execute this, hello, 0, 1, 2, 3, and 4 is the value. So we get back now a vector of strings as the values. And our context is test with another hash map in it with a different entry for each one of the things in our loop. So if we do this now, we can execute it, and we get this long string that's a string representation, because what did we do? Get back here? After we did all, we got back a vector of all of the values returned by each one of these functions that we handed it. And then we can we're doing a string on that. So there's a whole bunch of these sort of things that we have in the macro system. And let's go through this a little bit. So GenPlan is a pretty ugly macro. We won't go through it right now. It has some optimizations that will probably break in some situations, but work really well for us, so we won't worry about that. GetPlan is a wrapper that allows us, well, actually, let's just do that here, show that working. GetPlan allows us to do this. We do GenPlan, and then we can do GetPlan. And it's the same as executing and wrapping the function in the form. So then we have push binding, push alter binding, get binding, and pop binding. These are exactly what you would expect from the bindings macro in Clojure, but they don't go out and mutate some state somewhere or mutate a thread local state. Instead, what they do is they work with the context. So push binding says takes a key and a value, and it updates in. It calls update in on the context, and goes in and goes into the bindings and for a given key that we have, so we can have multiple bindings or kind of vars if you want to think of that, and conjuges a new value onto the list of bindings. And then if we get the binding, we just do the inverse. We give it a key, it goes into the context, and it gets in the bindings for the given key and gets the most recent item that we pushed up there with the conj, right? So we have this stack of values, and we can pop bindings as well and go back to the old state. So I found that when developing compilers and that sort of thing, a lot of the state that you need to keep track of is best done with stacks of values. So as you go up the stack, as you go deeper into your code, you're building up these stacks, and as you come out of the forms and return, you can pop the values off, and that works pretty well. All we talked about before just threads the context through all of the functions. Association, update in, get in work just like you would think with association, update in, and get in, but they work on the plan or the context. We have something that prints out the plan. Won't worry about that. So now we get to some interesting stuff. And we are going to take another little detour and talk about SSA form. So, what would be the best way to do this, actually? I think the best way to do this is to show a little bit of this code in action, what we end up with. So, the core, there's two phases of the Core.Async macro, Go macro. And the first one is we parse code into an SSA format, and I'll explain what that is in a second. And then the second is we put it all back together into Clojure code. So we're going to take this first part and play around with it a little bit. So let's start by if x1 and the environment has this, and the user has this. Okay. And we need some, let's do this. So we'll print this out, and then it'll make a little more sense. Okay. SSA format is a way of representing code in which you have a set of instructions that are organized in blocks. Every block has a single entry point. Every block has a single exit point. Multiple blocks can go into a single block, and a block can go out to multiple blocks. But they always go in the top of the block, and they always exit the bottom. All right. Within that block, all values are immutable. And what you do is you have a set of instructions that take as an argument the output of one or of none or more other instructions and produce a new value that can be consumed by somebody else. All right, so that probably doesn't make a whole lot of sense, but we'll take a look at it here. So this code right here that we're looking at, if x is equal to 1, then return true, else return false. There are essentially 4 blocks of code. We have the one consists of the preamble, or whatever comes before the condition, which in this case is going to be equals x1. That produces some sort of Boolean value. So we'll do it like this. So ID1 is x equals 1. And then we're going to do a conditional jump based upon the value of ID1. And this is not proper hash map format, but just ignore it. In the case that the ID1 is true, we're going to jump to block 2. Otherwise, we're going to jump to block 3. In block 2, we are so this is the way Core.Async uses the code, uses SSA format. It may differ a little bit for others, but we're going to use it in a certain way here. So within block 2, we say jump to block 4 and pass that block a value of true. And then block 3 says jump to 4 with the value of false. And then 4 basically says return value. So you can see here how we kind of have a diamond shape. The code comes in here, jumps to either 2 or 3, and then exits through 4. Now what's very interesting about this format is it's extremely simple. We can represent all sorts of semantics with this sort of code, with this sort of code format. In that, what if there was another if buried inside number 2? If we nested that, well then we would just simply go off and emit those as separate blocks that then jump to some common block, maybe let's say 5, and then 5 would somehow jump to 4 instead, right? So it's all a matter of keeping track of these states, what block you need to jump to when you're done with your current block, and how you want to move around. But more importantly, too, it's very easy to see how some variables are used. Let's do an example of that here. Well, in this case here, it would be easy to analyze this block and say, you know what, the out ID1 is used here, and it's used here, and perhaps it's used in some other blocks. So what Core.Async does is, and you know, we may need a little more of a better example for this. So let's get a little bit more complex. Let's do this. Let's do x equals 0 if x equals x5, then we want to return done. Otherwise, we want to take a value from a channel. We're gonna do like this. We're gonna take a value from a channel, and we're gonna recur with increment. So what this basically says is that, you know, let's make this a little more, making a little more sense. So we're basically going to send 4 values to this channel, 0 through 5, right? Okay. Let's pull this code out here. So if we pull the code out like this, we can see how we would represent this. We would do it like this. 1. Actually, we'll number 1. So block number 1 says x equals 0. And now we have a loop. So we have to create a new block. And we need to jump to that block. So we do jump to number 2. I like this format a lot better. I've never used this format for talking about this, but it looks and works pretty well. So we're just going to do an unconditional jump to number 2. Now, in number 2, we have to do some sort of node here, some way of saying we're going to recur to this point, right? So we're going to actually do what's called a phi node, and we don't really use these in Core.Async. We could. We do a dirty hack instead because we actually are mutating data. But if we wanted to, we do it this way. So x1 equals phi. And if we come from block, and what this says is if we come from block 1, then we want to use the value of x. And we'll fill this out later. So phi node says, look at where you came from and figure out the value of x1 based upon the previous, some variable in the previous block, right? So now we have x1. And now we do a comp values and equals compare, and we're going to compare x to 5. And then we're going to do const jump, just like we did before. And we're going to go to some block, which I'll call x. Oh, no, the const jump is on comp value, and we're going to go to some block x, otherwise we're going to go to some block y. So let's fill that out. So, in the case that it's true, which is block 3, we will say return done, right? Because we're completed sending this data. If we are in block number 4, and we can go up here. If we're in block number 4, then what we're going to say instead is we're going to put the value into the channel. So we will say temp. So all of these operations really need to be assigned to something. So this will probably be nil, but we'll do it like this anyway. We're going to call something called a custom terminator is what we call it in Core.Async, and actually that looks like this. So the custom terminator in this case is the put term, and we are going to pass it the block that it needs to jump to in the case that it completes, which we'll call x for now, and then we're going to pass it some arguments, c and x. right? So or x1, because we're using x1 way up here, and oh, you know what? We need x1 here. All right. So now we have another block called 5. And this now says jump to 5 after you've completed putting the value into that channel. And this basically says jump. This is defined a little bit differently. Actually, no, we'll do it this way. So we're going to jump to, we need increment of x first. So x2 equals inc x1. And then we're going to jump to number 2. And now we can go back up here and rewire this node to say if we come from block 5, then we want to use the value of x2. Okay. Wow, so that's a lot of weirdness, right? But there's something interesting here. And that if we look at this code, we could represent this in Clojure, right? These could all just be a let. Each time we assign something could be a let. If we had some sort of go-to, that would be neat to have, that we could jump up to some block, or we could jump to a different block, right? If we had go-to. No, we're never getting go-to, but we'll do a hack. And then we need a way of tracking these values, right? This is what everybody talks about when they talk about the Go macro being a state machine. This is basically a state machine. We have a whole bunch of blocks. We can start and stop from any state. If you look at these blocks as states, that's basically what they are. We can start and stop at any location, provided that we pass in the correct state that it needs. So here, all we need in this block is we need x and x2 to be able to do our job, right? So it's pretty easy from here to analyze this. If we have it in a data format, we could analyze it and look at it and say, what are all of the variables that we need to keep track of in some place? If we do that, it comes out that the values here are x1, are x, x1, and x2, right? Do we need to do anything with comp value here? No, it never escapes the block, so we don't need to do any work with it. So x, x1, and x2, right? So what we can do now is we could rewire this whole thing into this sort of format. So we do a loop, we do case off of the current state of state, or we'll do this block ID of state, right? And then we could have this be if it's 1, block 1. So we could emit some code there, and 2, block 2, and so forth. Now, we can put this in a let. And when some block finishes, so for instance here, when block 1's done, all we really need to say is something like this. We could say, we could save a set into our state. This is actually an array, that's why I'm using this a set type thing. It's a little confusing, I know, but this is actually a mutable operation. So a set into the state of x and give it the value of 0. And then what we do is we say a set state block ID is now 2. And then we're going to return a keyword called recur. And what that allows us to do is down here, say if identical, result and recur, then we are going to recur. Otherwise, we're going to return the result. So what we have now is basically a poor man's go-to. Now this looks horribly inefficient, right? We're going to keep jumping from block to block, but in reality, Hotspot is really, really good. Most JVMs are really fast. And for most of the work we do, the JIT kicks in and you really won't know that you're running some code in a block. Unless you're doing some really high performance code, which you probably shouldn't be doing inside a Go block anyway. All right, put that in a function and then we don't have to go to these transforms. So, it's about all I'm going to talk about the SSA format for today. I hope to do another thing about this later. But we can go back down here and translate this here to that format. And here's what we get, right? 6 blocks. Oh, what do you know? 5 blocks. Well, that's because, well, why do we have 6 blocks? That's a little bit weird. I would have expected... I think there's an ending block. Yeah, so the system here on the right, the actual system would create a final block that when we return, it doesn't really return, it jumps all the way down here because there's some cleanup that has to be done. But we can look here at what we have. So we enter in at block 1, and here we go. It assigns 0 to this instruction, and then it jumps. We don't have the types because these are records here, but I'll explain them as we go along. This says now jump to block 2. In block 2, it says compare the instruction that we assigned to down here to 5, and now jump and assign the result of that to 2736. Test 2736, jump to 4 or 5. In the case of 5, we go and we call this take, which gets translated. That's another problem too. We didn't hand it the proper terminators, so it doesn't know that this needs to start a new block. But whatever. So it's going to put into this, and then increment this value, and then recur to the block number 2 right here. Okay, so how does this even work? How do we go about translating this code, right? Let's pull this conversation back a little bit. I've explained why, how this works, why we kind of want this. We want this ability to pause and start execution at any time. But how do we get there? Well, at the core, IOC macros looks a lot like the code we looked at in the last video, right? We have 2 things called def multi. We have right here, item to SSA that says we have a cond. Remember we had the cond before? Well, we got even more now. We check and see if it's a symbol, if it's a record, if it's a list, if it's a map, a set, or a vector, right? And then we do different dispatches on that sort of stuff. So the easiest one to start off with would probably be something like map. So let's jump there. Well, actually, you know what? That cheats, doesn't it? What this basically says is that if we get a hash map, what we're going to do is turn it into this sort of format. So if we pass in 1, 2, 3, 4, it's going to turn it into hash map 1, 2, 3, 4. So that actually is not a good example. So if we get an S expression, which is here, I call list, then we have all sorts of fun stuff, because there's a lot of problems when you're doing macros like this, dealing with all the different cases when somebody may be a given variable may be a function. It could be a Clojure, or it could be a variable that's defined by a let or something like that. So this does a whole bunch of dispatching, and then finally says in here somewhere, sexpr to SSA. And what that does is down here, it's exactly what we had before. It takes the first item and then dispatches off of that. So let's say we had an if. What does that look like? Oh my, this looks fun. It's actually pretty simple. So let's get started. When we get into the first part of this plan, there will be a context somewhere, right? We're going back to GenPlan that we talked about before. There is this context handed to us, an existing context. And we are going to say, when you hand a context to this particular function, you better have a block that is set up to currently write to, right? So what we do is we say we take the test value go up into, call item SSA recursively, so we're recursing down, and do whatever you need to do with parse it, and give me back the ID of that expression. So if we look back at what we were looking at before, this is our test, right? Right here. We're saying, go compile this somewhere. So if that's nested 50 deep with a whole bunch of ifs and do's, it'll create a whole ton of blocks. We don't care. All we want to know is that when we get back, give me the ID of whatever the result was of the topmost expression, right? So now that's in test ID. So that would be like literally the symbol ID1 right here. And then we're going to add 3 new blocks, which on the right side are 2, 3, and 4. The then block, the else block, and the final block. So we just go and create those, but we have IDs to them. So we could jump to them and start writing whenever we wanted. So now we can write an instruction called conditional branch, and we pass it the test ID, the then block, and the else block. And conditional branch is a record that's defined up above. And I don't know if we'll get to that today, but in a further video we may. All right, so now we say switch to the then block. So now whatever anyone writes is going to be written into the then block. And we say then ID is item to SSA then. So we go and we compile the then side, which is this part right here, right? And that goes into that block. And we'll ignore that real quick. We'll come back to that in just a second. And then we set to the else block, right? And we do the same. And then down here, we go to the final block and we say, you know what? We want to return whatever value was handed into this block as an argument. True SSA doesn't really have this idea of an argument, but the Clojure semantics are simple enough that instead of doing phi's like we have down here, we work off an idea that there's a value that one block can pass to another block as an argument. In addition to that, in some cases, for instance, recur is a special instruction in this code on the left that I've developed that recur can overwrite values. And that's just for simplicity's sake. There's a whole lot of stuff that's really cool about phi nodes, but if you're not doing advanced analysis, I don't know that you need it. Alrighty. So, what is this here? Well, if you imagine something, that's a bit of a problem. So what we did here is we said item to SSA then. Okay, so now we have the then ID, and we need to terminate this block. So what we want to do is say add instruction jump then ID final block. So when we're done, we want to jump down to here and pass it the then ID as the argument, right? But what about in the case of our recur right here? If we go back down here, it says if identical recur. That's kind of a problem. Because if we were to, oh, sorry, that's the wrong form. Here we go, down here. So it says if x equals 5, we do this whole thing, and then we recur. Well, if we use the code on the left, then if, when it wrote in the instructions, would attempt to write a jump here to some unifying block. But that's not what we want, because recur has already told us we're going to jump to a different place. We're going to jump back up to the top of the loop. So what happens is that when recur does its work, it passes back as the value returned by item to SSA : terminated. And what that says is this block, this line, this path of execution has been terminated. You don't need to handle it anymore. We've already handled where it's going to jump. So if just says fine. So what happens is it says, hey, if it equals terminated, if it does not equal terminated, then go and emit your jump instruction. Otherwise, do a no operation. And the reason we have to do this is because everything in this GenPlan requires a function that takes a hash map, right? So no op does absolutely nothing, but it conforms to to the format that's expected here. Right. So that's if, well, here's recur. Let's take a look at recur real quick. Actually, the better place to start would be at loop. All right, so loop does some parsing, right? When you get done, what you get is a partitioned set of pairs of binding values, so x and 0, and it also gives you all the symbols, so x and a whole bunch of other stuff, and all the initialized values, which in this case would be 0. So what it says is, first thing we need to do is we need to emit this initialization, right? Up here we have this x equals 0. So we need to emit all of those. So for each one of these, do a GenPlan, get some ID for it, item to SSA, right? And then we push alter binding. So we say, go into the locals binding and associate in for this symbol item ID. So from now on, in any of the code underneath us that we dispatch from here until down here when we do pop binding right here. So all the code emitted in here, right, is allowed to access these locals. And then you see this little thing here called parallel bind. And what the reason behind that is there's a really interesting thing with Clojure that you can do this. X equals 0. Y is x plus x, like 53, right? So it's called, actually that's not a parallel bind. It's a problem with it being parallel bind. There we go. The old code had a problem before I added this fix in here, that it would basically try to, it would not provide x as a proper variable inside the context of this expression here. And that's a very subtle thing, and that it actually blew up and said, hey, I don't know what x is here, right? Because has x been defined by here, by this time or not? Or is it only within the body of the loop? Apparently in Clojure, this is valid code, so we support that. So we go in and say, hey, you know what? We have a new symbol available, and here's its ID, item ID. So now, this is interesting, if we go up to symbol here, so item to SSA, if we want to compile a symbol, we just do a GenPlan, we get all the locals, that binding, right? Get binding locals, and we say, if this variable is in the locals, right, then we're just going to emit the usage of that as the value. And I'm trying to think of a better way to say that. So what that means is that if we let's do this. Let's do what's the other default here? That's for the symbol. Yeah. So list here. There's a place where we go and we compile all of the, here we go, default. Like I said, this code gets a little bit interesting. Okay, so here is the case, right, where we have a normal function call like this that says +1, +2, and x. 42. So we're gonna compile this code right here. We're gonna look at how this code would work. So what happens is that in let, it says let binding to SSA. It calls let binding. Here we go. So it says for this one of these inner helper functions says, hey, we have a let. So we have an x and 42. The symbol is x. The binding is 42. So what we do is we emit item to SSA for 42, and that gives us back an ID, something that these can be used in these blocks. So we've assigned an ID to this 242. And then we say push alter binding, associate, and say, hey, anybody who wants X, now you have it. It's called bind ID. So now, if we go to default here, we have a bunch of args, and we do item to SSA for each one of these, and we have all the different IDs. for here we have plus, 2, and x. So it's assigned IDs to plus, to 2, and said, well, wait a minute, we need this ID for x. So remember, if we looked at what we looked at before was in symbol, it says go into the bindings, okay? We go into the bindings. If the bindings contain x, do they contain x? Yes, they do, and they have some sort of ID. Then return that as the value returned by this GenPlan. So we have inst ID here, and then we're going to return it down here. So when this is used in another GenPlan, the value they get is whatever that ID was that was in the locals map, right? And so from there, we can go up and do, go back to where we were, which was default sexper, and we get all of the argument IDs. So these are not the arguments, it's just all the IDs. So it may be something like ID 42, 43, and 44, right? And then we add a new instruction that has all of those IDs and returns the ID of our new instruction, which would be the result of this addition. So this is kind of delving more and more into compiler world, but that's kind of the gist of how these deep walking macros work. They all work in Core.Async. They all work by having blocks, and we create instructions in those blocks like that. So if we look at, go back to let here. So we do this for all the bindings. We add in the instructions for all the bindings, right? So it says item to SSA for this binding. Now we have the ID. Now let's push it. Now we go to the next one and the next one and the next one. Now that we've done that, then we can emit the body. And then we pop all those bindings. And because we've emitted the body, inside the push and pop, they have access to our bindings here, which is X, and so forth. Now, the key takeaway from all of this is that all of these things compose extremely well. Extremely well. And what this means is that we can have a lot of extensibility. Most of the times when I've hit bugs with the system, I can sit down and think about it for about 20 to 30 minutes and then find a 5-line change or a 3-line change that can completely alter the semantics of a certain part of the code and not require major refactoring. So let's see. This does not even get into how we emit the code, and that's a whole nother situation, a whole nother topic for a different day. But I would encourage you to go into this code and think about, yeah, try. So try is a big fun one. Maybe we'll deal with that one next time. But look at some of the common use cases. Recur, if, even do is a great one. So what do is really the simplest of them all, right? It says we have something and a body. GenPlan. Map, item to SSA for all the body. All of them? Great. Now we have a set of IDs, right? Because we had that all. We have all returns a vector of all the IDs, all the values returned by this item to SSA, right? So now that we have this vector of IDs, what do we want to be the value returned by the do, right? So if we have this, we'll print line 1, and then 2, which, if we emit all of these, and these all return values that represent the return value of these expressions, which one do we want to return to the caller? Or the person up, the enclosing expression. I guess you'd call it a caller, it's kind of that way. But which one do we want to return? Well, it's the last one, right? So we do the last of IDs. That's all it takes. If for some reason we wanted different semantics there, we can use normal S expression stuff to completely alter this. There's no big deal there. Let's see, what other ones? If, we talked about if, loop. Function gets a little bit interesting. We'll handle that later. Okay, so as a closing part for today, a closing thing for today, let's look at the output of this right here. So if we import Core.Async, and we get some, some warnings there. Let's take a look at what this code looks like. This code we were looking at before. And it's complaining no such var, it doesn't have C, we need to actually define that. Oh, actually, let's do this macro expand. This, and then Clojure dot. All right. So here is the major amount of code that we have here, right? But let's take a quick look at it. So we're going to assign 0 to this value, and then we put it into an array called state in the 6th position, right? So there's in Core.Async, we represent the local variables that we need to save from one block to another as a mutable array of objects, right? And we just stow away the value we created here, 8248, right? And then we say here we want to recur with the new state value be here, so the new state value being 2. And like I said before, it goes down here and says if identical to recur, go back up to the top. And so we have all 7 states. We have a loop with a case statement, like I mentioned, which I think actually gets compiled to a jump table by hotspot, so it's pretty fast. And it's just all a matter of, in each place, any variables you need for that block, unpack them from the array, do your work, put the new values back into the array, find out where you're going to jump to next, and then recur based upon that. Except for the time we take from, or put in the channel here, sorry, which is right here, in which case we end up calling put, which should be right here. So because we represent our state as a mutable array of data, we can simply call IOC macros put and say, hey, you know what? Here's an array that you can muck around with and change the state of the state machine. When you're done, try to jump to block number 7, if you will. And here's the arguments of that terminator. So the terminator here of the block was C and X1, and so it hands it these. Where does 5284 come from? Oh, well, 5284 comes from up here, which we pull out of that same mutable array at position 6, right? Which we wrote to position 6 right up in here. And initialized it with a value of 0. Okay, so next thing that we need to look at then is, real quick, we're going to look at this put. So let's get back to that put, wherever that was. Here we go. So it's going to call this function. So put takes a state, which is an array of objects, a block to jump to when we're done with whatever we're doing, and any arguments that were passed to this terminator. So what we say is go into the Core.Async stuff that everyone's used to, an async operation, create a function, and we're going to put into a channel with this value and have a callback. And we're going to attach a callback to that channel and say, hey, you know what? When you're done, set the next state that we want to jump to be the block that we were handed, which is 7 here, right? And then we're going to run the state machine again, handing it the mutable array. So that right there is the guts of Core.Async. I'll try to do another video soon that deals with how we generate this actual Clojure code. But I would encourage you to take a look at this code on GitHub and look it over a little bit more. Hopefully this tutorial was helpful to some people. I would imagine at this point, if you are really motivated, you could take a look at IOC macros in the Core.Async repo and pretty much figure a lot of it out. Some of the stuff around trying exceptions and that sort of thing gets a little bit convoluted, but for the most part, when I've gone over a tutorial like this with people in the past, they've been able to sit down and within about half an hour after this pick up at least enough of the code to be able to get a grasp on how it works and stuff internally. So once again, thank you for listening. My name is tbaldridge, and I'll have some, hopefully do some videos like this again soon in the future. Thanks. Bye.